Good day everyone. Today we will be presenting on the origin of color in transition metal complex. This topic explains why many transition metal compounds appear brightly colored and how their electronic structure plays an important role in producing these colors. Firstly, let me introduce our team members. First, my name is Putrilia and we have Nur Atira Natasha, Nur Hazwani, Putri Nur Asha Ashikin and Muhammad Danish Aiman. Transition metal complexes exhibits color mainly due to their partially filled d orbitals. Unlike main group elements, transition metals have d orbitals that can participate in electronic transitions. When ligands approach and surround a metal ion, they create an electrostatic field around the metal. This interaction causes the degenerate d orbitals to split into two groups with different energy levels, a phenomenon described by crystal field theory. When visible light shines on a transition metal complex, electrons in the lower energy d orbitals absorb specific wavelengths of light and become excited to higher energy d orbitals. Only certain wavelengths are absorbed, while the remaining wavelengths are either reflected or transmitted. The color that we observe is actually the complementary color of the light that has been absorbed. Therefore, the specific color of a transition metal complex depends on the energy difference between the split d orbitals, which determines which wavelengths of light is absorbed.
Transition metal complexes are well known for their bright and varied colors, such as blue, green, and yellow. The origin of these colors can be explained using crystal field theory. According to this theory, when ligands surround a transition metal ion, electrostatic repulsion occurs between the ligands and the d electrons of the metal ions. This interaction causes the 5d orbitals to split into two different energy levels instead of remaining degenerate. The separation between these two energy levels is known as the crystal field splitting energy. This splitting is the key factor that links crystal field theory, the origin of color in transition metal complex. When visible light shines on a transition metal complex, the light contains many different wavelengths. However, only light with energy equal to the crystal field splitting energy is absorbed. When this absorption occurs, an electron in the lower energy d orbital is excited to a higher energy d orbital. This process is known as a d-d electronic transition. Since only specific wavelengths of light are absorbed, the remaining wavelengths are reflected or transmitted. As a result, the color that we observe is the complementary color of the absorbed light. Therefore, crystal field theory explains the origin of color in transition metal complex through a d orbital splitting and the absorption visible light.
Delta refers to the energy gap between the T2G and the EG orbitals in a transition metal complex. When ligands surround a metal ion, the d orbitals split into two different energy levels, with T2G at lower energy and EG at a higher energy. The size of a delta determines how much energy in the form of light is required for an electron to move from lower T2G orbital to the higher EG orbital. This energy absorption is what later contributes to the color observed in the complex. The size of delta directly affects the color observed in a transition metal complex. When delta is large, a greater amount of energy is required for an electron to be excited from the lower T2G orbital to the higher EG orbital. As a result, the complex absorbs high energy light with a short wavelength such as violet or blue light. The color that we observe is the complementary color, which is typically yellow, orange, or red. On the other hand, when delta is small, less energy is needed for the electron transition. In this case, the complex absorbs low energy light with a longer wavelength, usually in the red or orange region, and the observed color is the complementary color such as blue or green.
Without ligand, all 5d orbitals have equal energy. However, when ligands surround the metal ion in an octahedral arrangement, the d orbital split into two groups. the T2G orbital are lower in energy, while the E9 orbital are higher in energy. The energy difference between these two levels is called delta. When the white light shines on the complex, one specific wavelength of light is absorbed. This absorbed energy promotes an electron from the lower T2G orbital to the higher E9 orbital. These remaining wavelengths are reflected back to our eyes. Therefore, the color we observe is the complementary color of light absorbed.
There are three main factors that affect the color of transition metal complexes. The first factor is the type of ligands surrounding the metal ion. Different ligands cause different degrees of d orbital splitting, such as strong field ligands produce a larger delta leading to absorption of higher energy light, while weak field ligands produce a smaller delta and absorb lower energy light. The second factor is the oxidation state of the metal ion. A higher oxidation state increases the attraction between the metal ion and the ligands, resulting in a larger delta and a shift in the wavelength of light absorbed. The third and last factor is the identity of the metal ion itself. Different metal ions have different electron configurations and orbital energies, which influence the size of delta and therefore the color observed, even when bonded to the same ligands. Ligands can be classified based on their charge and the way they bind to a metal ion. In terms of charge, ligands may be neutral, anionic, or cationic. Neutral ligands have no overall charge, such as water or H2O, also known as aqua, and ammonia in H3, known as amine. Anionic ligands carry a negative charge with common examples including chloride Cl- and bromide Br-. Cationic ligands are positively charged and are less common, with nitrosyl NO+ being a typical example. Ligands are also classified by their denticity, which refers to the number of donor atoms that attach to the metal ion. Monodentate ligands bind through one donor atom, while bidentate ligands bind through two donor atoms, such as ethylene diamine and oxalate. Polydentate ligands bind through more than two donor atoms, with EDTA4- being a well-known hexadentate ligand. The type of ligand significantly influences the stability and properties of coordination complexes.
Next, we move on to visual explanation of color formation of metal complex. So first, we need to understand why complex ion has colors. Complex ion has colors because they contain transition metals with partially filled d orbital. When ligand approach metal ion, the 5d orbital no longer has the same energy. This causes the d orbital to split into different energy levels. As a result, electron can absorb visible light and move between these orbitals. This electron movement is called a d-d transition, and this is what produces color.
Visible light is made up of different colors, each with specific range of wavelength. At the shorter wavelength and higher energy end of the spectrum is violet, which wavelengths approximately 380 to 450 nanometers. This is followed by blue light, which range from about 450 to 495 nanometers, and green light with wavelength between 495 and 570 nanometers. Yellow light lies in the range of 570 to 590 nanometers, followed by orange light, which has wavelengths of around 590 to 620 nanometers. At the longer wavelength and lower energy end of the visible spectrum is red light, with wavelength between 620 and 750 nanometers. In transition metal complexes, the color observed depends on which of these wavelength is absorbed, and the color we see is the complementary color of the absorbed light.
Ligand strength play an important role in determining the value of delta. Weak field ligands such as water or chloride cause small splitting, resulting in pale colors. Strong field ligands such as ammonia or cyanide cause large splitting, which leads to deeper and more intense color. For example, in the complex ion nickel H2O6 2 plus, water is weak field ligand. So the splitting is small and red light is absorbed, making the complex appear green. In contrast, nickel and H3 6 2 plus contain ammonia, a strong field ligand, which cause larger splitting and absorption of yellow light. So the complex appear deep blue. This shows that the same metal ion can have different color depending of the ligand. In conclusion, the color of complex ion is caused by D-D transition, which depends on crystal field splitting, ligand strength, and the energy of light absorbed.
For this slide, I will explain about the real-life application and its example. But first of all, did you know actually the color is already exists in our daily life? Everywhere we go and everywhere we see, they always color, right? For example, we can take as a wall piece and ink printing. It can be categorized as pigments and dyes. Other than that, we can also see color in the gemstone or in the jewelry that we always wear. Other than that, if you like science, you should know that they're also colored when you're doing an experiment. And for the last one, it's really common in our country and in another country too, which is color glass and lighting, which could be found at the traffic light. Example that we can use for pigments and dyes category is cobalt pigments. This cobalt pigments is show a blue color. This happens because transition metals complex absorb specific wavelength of light, producing strong and stable colors that are widely used as a pigment. The next one is a gemstone. When we think about gemstone, we know a ruby and emerald is a type of it. Ruby color is red while emerald color is green. This base crystal is colorless, but a small amount of transition metal ions absorb certain wavelength of light, giving gemstone their color. Other than that, for the qualitative analysis, which is in experiment, I take two examples, which is copper sulfate and potassium permanganate. Copper sulfate can appear blue in aqueous solution. This characteristic blue color is used to identify the presence of copper ions in the laboratory analysis. While the potassium permanganate, which color is deep purple, is useful as a self-indicator in titrations and for identifying oxidizing agents. And for the last one, for the color glass, I take example is chromium doped glass, which is indicate the color of green. This has happened because transition metal ions in glass absorb selected wavelength of light, producing a permanent colors.
In conclusion, the color of transition metal complex arises mainly from electronic transition within the d orbitals of the metal ion. When ligands approach the metal ion, they cause the d orbitals to split into different energy levels. When visible light is absorbed to promote electrons between these split levels, the remaining reflected or transmitted light gives the complex its observed color. The exact color depends on factors such as the type of metal ion, its oxidation state, the nature of the ligands, and the geometry of the complex. Therefore, the vivid colors of transition metal complex are a direct result of their electronic structure and metal-ligand interactions, making them important in both chemistry and practical applications such as pigments, indicators, and catalysts.